In less than an hour, we'll finish our 6th month out of Cape Kennedy. 6 months in deep space. By our time, that is. According to Dr. Hasline's theory of time in a vehicle traveling nearly the speed of light, the Earth has aged nearly 700 years since we left it.
If we're going to travel for 6 months on a spaceship while Earth has aged 700 years, assuming that we have been traveling at that constant speed for all that time, at which speed do we need to go, do we need to be traveling so that we have that time dilation factor? So the time elapsed on the spaceship is T0, 6 months, half a year. The time spent on Earth, it's T, which is 700 years. The relationship, the time dilation relationship is that T is equals to T0 over the square root of 1 minus beta squared. Remember that beta is V over C. So now we want to solve for beta, so we square everything here. T squared is equals to T0 squared over 1 minus beta squared. We put this on the other side. This is going to be 1 minus beta squared. It's going to be T0 squared over T squared. Then I solve for beta. Beta squared is going to be 1 minus T0 squared over T squared. Therefore, beta is going to be the square root of 1 minus T0 over T squared. So let's come here, let's substitute, and we find that beta is going to be something like 0.999999744. So basically the speed of light. If you want to know what's the difference between that speed and the speed of light, we can make 1 minus beta. Remember that beta is V over C, therefore 1 means that the velocity is C. So 1 minus beta is 2.55 times 10 to the negative 7. So that's how close it is to the speed of light. And here, let me introduce a new parameter, a new constant, because we're going to see this 1 over square root of 1 minus beta squared very often. I'm going to define gamma as precisely that, 1 over the square root of 1 minus beta squared. So really need, in order to have that important time effect where gamma is, if you look at here, this is gamma is going to be T over T naught. So we're going to have a factor of gamma of 1400. In order to have such an important time dilation, the speed needs to be almost the speed of light. Of course, this problem has some assumptions that we have not mentioned. For example, in order to go from rest on Earth to that speed, the spaceship and the astronauts need to accelerate. We have not considered that, but because in the process of acceleration, the speed is smaller than the cruise speed, the time dilation in that process of acceleration will not be as strong as in cruise speed. So this is just a rough estimate. Enough though to see that important effects on time really need incredible speeds. Let's solve now another problem. Let's determine the contraction of the diameter of the Earth in the plane of the ecliptic for an observer at a reference frame S prime at rest with respect to the Sun. Consider the diameter of the Earth as measured from Earth to be 12,700 kilometers and the speed of the Earth around the Sun to be 30 kilometers per second. We know that the length contraction expression is d, the diameter that observer is going to observe from its reference frame S prime, is going to be d naught times the square root of 1 minus beta squared. So remember that we have that the diameter of Earth, d naught, is approximately 12,700 kilometers, and that the speed of the Earth around the Sun is approximately 30 kilometers per second. That said, we're looking for delta D, which is just the diameter of Earth minus this diameter that is going to be observed from the other reference frame. Remember, we have a reference frame here on the Sun, and the Earth is moving at that velocity v around the Sun. So, well, let's calculate that delta d. So delta d is equals to d naught minus d, and that is just equals to d naught bracket 1 minus the square root of 1 minus beta squared. That is going to be the change. Now, because beta, we know that beta is going to be very, very, very small. I mean, the speed, this is 30 kilometers per second, and is just 1,000 times smaller than the speed of light. So because beta is way smaller than 1, I'm going to approximate this square root as an expansion in series of Taylor. So for beta very, very small, smaller than 1, I have that 1 minus beta squared. This square root, oops, it's going to be approximately 1 minus beta squared. That said, I know that delta d now is going to be d naught, and then this thing here is going to be that 1 minus this, minus 1 minus beta squared, which this is basically d naught beta squared, depends on the square of the speed of the Earth. Now we know what beta is. Beta is that 3 times 10 to the 4, which is the speed of the Earth, divided by 3 times 10 to the power of 8, which is 10 to the negative 4. And if we substitute that, we get the delta d. It's, and you can do that with your calculator, 0.137 meters, which is 13.7 centimeters. Really, really, oh, sorry, that's a 13. Let me do it properly. So we see that the effect of relativity for these daily speeds is really, really negligible. This calculation demonstrates again that the speeds required so that relativistic effects need to be considered are really high. They need to be comparable to the speed of light. Depending on the problem at hand, some important effects can start to take place at 15–20% of the speed of light. Although when we talk about the GPS, we will see that even smaller speeds can have an impact, depending on the resolution of your measurement.